Hello. Let's talk about magnetic force in current-carrying wires.
When an electric current flows through a wire, something interesting happens. It creates a magnetic field around the wire. Picture it as a concentric circle surrounding the wire. With their direction determined by the right-hand rule, the strength of the shape of this magnetic field depends on the factor like currents, magnitude, direction, and distance from the wire. Now, if we introduce an external magnetic field and place our current-carrying wire within it, the magnetic field generated by the wire interacts with the magnetic force being exerted on the wire. We can call this force the magnetic force or the Lorentz force.
The Lorentz law helps us understand this phenomenon better. It tells us that the magnetic force, or F, acting on the wire can be calculated using the equation F is equal to I times B times L. Here's what that means. The magnetic force is perpendicular to both the direction of the current I and the magnetic field B. To determine the direction, we can use the right-hand rule. Imagine pointing your thumb in the direction of the current and your fingers in the direction of the magnetic field. The force will then be in the direction your palm faces. Now, let's talk about the magnitude of the magnetic force. We can calculate it using this equation. The absolute value of F is equal to the absolute value of I times the absolute value of B times the absolute value of L times sine of theta. In this equation, absolute value of I, B, and L represents the magnitudes of the current, magnetic field, and wire length, respectively. Meanwhile, theta represents the angle between the current and the magnetic field vectors. It's worth noting that It's worth noting that the magnetic force only acts on moving charges or current-carrying conductors. This is because the force arises from the interaction between the magnetic field and the charge in motion. If the charges are at rest or static, only electrostatic forces governed by Coulomb's law comes into play. Magnetic forces.
The direction of the magnetic force is given by the right-hand rule. If you point your thumb in the direction of the current, your fingers will curl in the direction of the magnetic field, and the force will be perpendicular to both the current and the magnetic field. The magnitude of the magnetic force depends on the strength of the current, the length of the wire segment within the magnetic field, and the strength of the magnetic field itself. The force is directly proportional to the current and the magnetic field strength, and is also affected by the angle between the current and the magnetic field.
The magnetic forces in current-carrying wires have practical applications. For example, they're utilized in electronic motors where the interaction between the magnetic field produced by the current-carrying wire and the magnetic field from permanent magnets causes the wire to experience a force and leads to rotational motion. Magnetic forces are also crucial in devices like solenoids, transformers, and magnetic levitation systems. It's important to note that magnetic forces are distinct from electrostatic forces, Coulomb's law, which describe the forces between the electric charge at rest. Magnetic forces only act on moving charge on currently carrying conductors and are a consequence of the magnetic field created by the current.